So good day, everyone, and welcome to class. Good, good, good. So we're going to run through activities today. I understand exams have been scheduled for February, and we're going to be having so many activities running through the week. And I also understand some of you will be, okay, well, you won't be convocating tomorrow, next week. So we may be having our lecture next week, but I understand some of you may want to celebrate with one or two persons while, the final year students are convocating. So we'll see how we'll be able to manage our activities so as to cover up a few details. But today, we'll be covering concepts in transforms, okay? Is that clear? Is that okay?
Yes, sir.
Good, good, good. Okay, so I'll just begin.
Sorry, I didn't get that, sir.
You what? What did you say?
I didn't get what you said, sir.
Well, I said we'll be covering concepts in transforms today. I understand your exams have been scheduled for February. So we want to try as much as we can to cover a few areas and then begin with the class revisions before your exam. Okay? And I also understand next week is convocation week. So we'll see how we'll be able to manage our class activities for next week. Is that clear? Is that clear?
Yes, sir. Yes, I said.
Okay.
Yes, sir.
Okay. So when we talk about transforms, so okay, so we say transforms. Oh, this one, this two. So when we talk about transforms, we have two things in mind, okay? And the two things we have in mind is either continuous time or discrete time. And when we talk in terms of continuous time, we talk about Laplace transform. And when we talk in terms of the discrete time, we talk about Z transform, okay? And when we now talk about the scaled version, where we have to play with strictly signal processing in terms of the frequency component or content, we talk about Fourier transform for continuous time systems. And for the discrete time systems, we'll begin to talk about the discrete Fourier transform, okay? As a discrete Fourier transform. And in more specialized signal processing systems, we talk about the fast Fourier transform. It's a faster algorithm, right? The fast Fourier transform. Okay. Which is an improvement on the discrete Fourier transform, but a faster algorithm. Okay, so we'll try to run through these transforms today. And then afterwards, we begin to look into applications. So we already know that transforms in general are used for transforming from the time domain to the frequency domain, okay? So and vice versa. So if the Laplace or Fourier or Z transform moves from time to frequency domain, then the inverse Laplace transform, inverse Fourier transform, then inverse Z transform moves from the frequency domain to the time domain. So basically, transforms are used for switching between time domain and frequency domain representation, okay? So that's what it does, okay? Switching between time domain and frequency domain representation. Okay. So in as much as we have the transform, we also have the inverse transform. Okay. Transform. So while one moves from time to frequency, the inverse moves from frequency to time. So perfect. So that's a simple representation of what we are going to be talking about. And I understand most of you have been able to look up the notes we have online. So well, this would be more like a crash through exercise. Okay, so let's begin with Laplace transform. So Laplace transform is a tool. Okay, now we already mentioned what transforms mean. So Laplace transform in this case is a tool used for switching between time domain and frequency domain representation. Okay, and as such, we see that it is used for the decomposition of continuous time signals into the sum of complex exponentials. Okay, and we already know that a system characterized, a continuous time LTI system characterized by the response h of s fed with the eigenfunction EST, we produce an output response, which is a scaled version of the eigenfunction. Okay? And here, the eigenfunction EST is an input to the continuous time linear time invariant system. And the output is a replica of that, which is this, but a scaled version. Okay? And from this, we see that the Laplace transform is the sum of the complex exponentials, okay? Is the sum of the complex exponentials that are the eigenfunctions of the LTI system, okay? And that implies that the Laplace transform can be used to evaluate the output of any type of input due to the ease of evaluating the eigenfunction, okay? So shortly we'll see that all transforms cannot be used to analyze all signals, but we see that Laplace transform can be used for the analysis of energy signals. It can be used for the analysis of power signals, and also for the analysis of neither energy nor power signals. And by definition, we have two forms of Laplace transform: the bilateral or the two-sided Laplace transform, and the unilateral or one-sided Laplace transform. And the difference is on the limits of integration. For the bilateral Laplace transform, it takes on limit from negative infinity to positive infinity. While the unilateral Laplace transform takes on limits, the limit values from 0 to positive infinity, okay? But in practical systems, we want to adopt the unilateral Laplace transform because we are not able to deal with negative time, okay? So in practice, we're on the positive scale. But for us to be able to develop the theoretical background for system analysis, we usually adopt the bilateral Laplace transform for analysis, okay? Okay, so now go away. I think the echo. Is it better now? Can you hear me?
Yes, sir.
Okay.
Yes, sir.
Okay.
Yes, sir.
So, since we already established that a system can be characterized by the response lambda, for which the input is an eigenfunction, such that the output is the scaled version of the eigenfunction, we see that the output, in this case, y of t, is the same as lambda est, okay? And this is the same as h of x est. Since lambda is the eigenvalue of the eigenfunction, then it means that h of s is the same as the eigenvalue. Okay? So we are saying now that lambda is the eigenvalue associated with the eigenfunction, est. Okay? And in this case, s is a complex variable. Okay? So, but you also recall that the output of an LTI system is described by the convolution of the response of the system and the input, right? Such that y of t is the same as h of t convolved with s of t, which is now the same as what we described last time. The convolution is a integral taking a limit from negative infinity to positive infinity, h of tau, s of t minus tau, which is the delayed version of the sigma d tau. Okay? Yeah, I can see one hand up. Okpara Wilson. So we can spare 1 minute.
Please, I didn't understand like this eigenvector, the eigenvalue part, but I didn't understand what you were saying there before you moved on.
Okay, that's fine. So, well, I think we made mention of that in our last class, okay? That given an LTI system, the input to an LTI system is the eigenfunction, which is described as EST. And by the time you decompose EST, you see it's the sum of sinusoids, right? We have the epsilon ST is the same as cos and the cosine function and the sine function, okay? So what we're trying to say is that this system, from what we analyzed previously, the LTI, you want to look up the LTI lecture, okay? Now, once we try to feed in an input to the LTI system, we see that this is the input. Now, this is the output. We see that the output is a scaled version of the input, only that what scales the input is the parameter that describes the system, which is the impulse response of that system, right? And from our previous analysis, we're able to tell that, well, that value that scales it at the output, we had an example also, is the eigenvalue, okay? Because every eigenfunction is associated with an eigenvalue, okay? Now, this eigenvalue itself, that's this eigenvalue itself, is the same as the response of the system. Now, Wilson, is that clear?
Yes, sir, I think so. So you're saying that this eigenvalue is the same as the impulse response, that's h of t or h of s.
Exactly, it's the same as h of s.
Okay, thank you, sir.
Yeah, so that's what characterizes the system. Okay, yeah. So, Dejo, I can see your hand up. So we can spell.
Okay, sir.
Okay, go ahead, please.
Yeah. This, from what you wrote, so y of t is equal to h of t convolved with x of t. Normally, what you used to write is x of t convolved with h of t, then is equals to integral from infinity to negative infinity x of tau h t minus tau t tau.
Yeah.
I don't know why.
Now,
I don't know whether is it commutative. Is it something you can say?
Okay.
A plus B is equal to.
I think I get your point. I get your point. Yeah, I get your point. Now, you want to look up the lecture on convolution. We talked about the properties of convolution, right? And we talked about linearity. So h of t convolved with s of t is the same as s of t convolved with h of t. Does that answer your question?
Yes, sir. Thank you so much.
Yeah, so it's the same thing. So by the principle of linearity. So probably you want to review the lecture note on convolution. So we made mention of that as one of the properties. Okay, so we're still saying the same thing. So we're going to get the same outcome. Is that okay? Okay, so now we try to move on. So if this is clear, now we know that S of t is the same as the eigenfunction est. So how about the time delayed version of the signal S of t? So it's going to give us the time delayed version of the eigenfunction, which is S of t minus tau, right? Because the time value has been delayed, right? So this is also delayed. The time value is also delayed. So this is also delayed. So once we plug that into this expression, what are we going to get? Now, you should also note that this expression, if you recall your laws of indices, logarithm, and the likes, is the same as est times e minus s tau, right? So we are writing the same thing. So we can actually plug in this expression into y of t. So we can plug in this expression into y of t and then come up with the expanded form, okay? So y of t will now be the same as integral negative infinity to positive infinity, h of tau. So recall we are replacing this with this expression, which is going to be est e minus s tau d tau, right? And now we see that we are actually integrating with respect to tau. So it means that this expression will be constant. This is going to be a constant because we are actually integrating with respect to tau. So then y of t will now be the same as integral negative infinity to positive infinity, h of tau, epsilon st, e. Okay, sorry, I think I just grouped them wrongly. Sorry for that. So here we have this and this are in terms of tau, right? So we want to group them, okay? So once we group them, because this is t, so this is with respect to tau, this is with respect to tau. So once we rearrange, so we have h of tau, e negative s tau, d tau, right? This is the tau, all in brackets, times est. Okay? So from this expression, we see that integral h of tau, epsilon minus s tau d tau, if this is the same as lambda, which is the same as h of s, then y of t will be the same as lambda est. Okay? Now, you observe that this expression is the Laplace transform of this system. Okay? So technically, we have now seen that the eigenvalue of the continuous time LTI system, which is associated with the eigenfunction, is the same as the Laplace transform of the impulse response. Is that clear?
Yes, sir.
Okay. Now, if that is clear, we can quickly move on so that we can now describe the bilateral Laplace transform to be defined as S of S being the same as negative integral to positive integral S of t epsilon minus st dt. Okay, so in this expression, we already mentioned that S is a complex variable. It's a complex variable that is described as the sum of the damping factor and the frequency or angular frequency. We know that the angular frequency is measured in radians per second, and this is the damping factor, right? The damping factor. Why this omega is the frequency, or better still, angular frequency. Now, this damping factor is very critical in analyzing system stability, as we'll see shortly. Because with this factor, with this sigma, the damping factor, we are able to determine the region of convergence, okay? Now, if this describes the bilateral Laplace transform, then the unilateral Laplace transform, S of S, will be the same as taking on limits from 0 to positive infinity, S of t, e minus st dt. Okay? Now, in the same vein, the inverse Laplace transform will be the same as S of t moving from the frequency domain to the time domain. Usually we say, well, we use this to describe the inverse Laplace transform of S of x will be the same as 1 over 2 pi j integral sigma negative j to infinity to sigma plus j infinity S of s epsilon st ds. You observe that for the inverse Laplace transform, the exponential function does not have a negative sign, but for the Laplace transform, it has a negative sign. We're integrating with respect to the frequency domain because we're already in the frequency domain, moving to the time domain. But to get our Laplace transform, since we are moving to the frequency domain from the time domain, we are integrating with respect to time. So Alozie, tell us.
Good morning, sir.
Good morning.
Yeah, I don't quite understand the IoT inverse Laplace transforms.
Okay.
You did L inverse, if I'm saying that correctly. I don't know.
Is it what?
I don't. That sign that
Okay,
you
this
did
is
L.
okay. It's a symbol to tell us this is inverse Laplace transform. It's just L inverse. To say,
Okay.
well, it's a symbol. Okay, so writing this just says, well, we want to take the inverse Laplace transform.
So that means it's equals to 1 over 2 pi j.
Yes, yes.
What's 2 pi j? What's j?
Okay, it's J is it's a complex number, right? But this is the
Okay,
formula.
okay.
Yeah, J is a complex number. This is the formula. But there's a bailout here because using this formula to evaluate the inverse Laplace transform could be very cumbersome. So we hardly or rarely use this, okay? So, but
Yes,
this is for your information. So what we use to evaluate the inverse Laplace transform most of the time is the Laplace transform pair, okay? Transform pair, okay? So we have a pair, you know, some formulations to say, well, the Laplace transform of this is this. So if you have this formulation, just know this is it, okay? So they are pairs. So oftentimes we want to invoke those pairs to evaluate the inverse Laplace transform, okay? Because integrating at this level could be very, very, very cumbersome, okay? But
sorry, sir. What were your upper and lower limits for the integral for the ILT? Is that R plus J infinity?
oh, it's sigma. This is sigma, the damping factor, sigma.
I thought that was R.
No, it's not R. It's sigma, sigma, sigma. The name of this symbol is sigma. It's not R. Sigma. Okay, so that's why we call it the damping factor. Okay.
Sorry, sir. Did you call it damping factor or what is it?
Damping factor is sigma. Okay. Why this is the angular frequency omega, not W. Is that clear? Is that clear?
So I have a
Yes.
question.
Okay, what's the question?
When we were doing the first one, that we said the like lambda is the same thing as each of us. We used negative infinity to infinity. So I was thinking that are we doing bilateral Laplace transform that time?
Use negative infinity to positive infinity. Well, if we're
On the
taking,
former slide before you came to this.
okay, if we are using
Infinity,
negative
yes.
infinity to positive infinity, we are on a bilateral plane because we are moving from the extreme of negative infinity to positive infinity. But unilateral takes on from positive 0 to positive infinity. Okay, so we are looking at the plane. Okay, this is negative infinity, this is 0, then this is positive infinity. Okay, so in practical systems, do we really have negative time? Do we have negative time? Now, let's take your clock, for instance. It keeps ticking in the clockwise direction, right? What if we try to make it tick in the anti-clockwise direction? Can we go back to our past? Yeah. So probably, who knows? You may be able to devise a technology that will be able to make the Earth rotate and revolve backwards in the reverse direction. And probably if you're able to do that long enough, we may be able to go back to the age when our forefathers existed and then reverse time, right? So who knows? You may want to alter the magnetic positioning of the Earth so that it will rotate and revolve backward around the sun. Who knows? We may be able to unwind and rewind our memories and go back to the past. Maybe we'll be able to come back to the good times when there was no wars and crisis. Okay? But in reality, we want to play with positive time. Okay? So I think that's the idea. I don't know if I've been able to address what you asked. Is that okay? Can we move on?
Yes, we can move on.
Okay, so looking up the inverse Laplace transform, you now see that this shows that a signal, say S of t, could be expressed as the sum. You know, the integral is the same as the sum of an infinite number of scaled exponential components. These are scaled exponential components, you know, and the signal S of t and its Laplace transform, like I said, forms the Laplace transform pair. And when we talk about the Laplace transform pair, we say S of t forms a pair with S of S, sorry, S of S, where this is the time domain and this is the frequency domain, okay? So in evaluating our inverse Laplace transform, we're going to be playing with the transform pairs, okay? So you have nothing to worry about. So what you want to play with, where you could derive them, then try to memorize them, okay? But it's not a big deal anyway. So let's assume we are given S of S to be the same as negative infinity to positive infinity S of t, E minus st dt, such that for all values of S being the same as sigma plus j omega. Okay, so S of S here is the same as the integral taking on values from negative infinity to positive infinity S of t, epsilon minus, so S is the same as sigma plus j omega, sigma plus j omega t dt. And then we could expand this negative infinity to positive infinity S of t, epsilon minus sigma t, epsilon minus j omega t dt. Okay? And then in the same vein, we say integral negative infinity to positive infinity, S of t, epsilon minus sigma t, epsilon minus j omega t dt. Now, you'll observe in this expression that for Laplace transform to exist, this particular expression has to be absolutely integrable, okay? This has to be absolutely integrable, okay? And by so we now say that, let me write that more appropriately, for Laplace transform to exist, St E minus sigma t has to be absolutely integrable. So that means that by the time we take the integral from negative infinity to positive infinity, mod S of t, epsilon negative sigma t, the t has to give us, should give us a finite value, okay? So it means that for this integral, coming, now for this integral to be, absolutely integrable, then we must figure out the value for which sigma is finite. Okay? Now, this is the interesting part when playing with Laplace transform. So I really need to take note right now. Okay? Now, we've been able to decompose the Laplace transform such that we have been able to separate the exponential function that is dependent on the damping factor and the exponential function that is dependent on the frequency. And now we are saying that the signal multiplied by the exponential function that is dependent on the damping factor has to be absolutely integrable. And for that integral to be absolutely integrable, to give us a finite value, then that finite value must exist at some value where sigma, the damping factor, is finite. Okay? So therefore, this damping factor sigma tells us everything we need to know about the region of convergence. Okay? So it gives us the information about the region of convergence. And when we are able to tell the region of convergence, then we'll be able to tell if the system is stable or not. Okay? So the region of convergence, therefore, is a region on the x-plane where the Laplace transform is finite. Okay, let's put that up here. So
Please come again, sir.
the region of convergence is a region on the x-plane where the Laplace transform is finite. Okay? So let us look at one simple example. Let's assume S of t is the same as E minus 2t u of t. And now we want to evaluate the Laplace transform. So what is the Laplace transform of this? So we already know the formula for our Laplace transform, which is S of S is the same as integral negative infinity to positive infinity, S of t, epsilon minus st dt. So we know what st is. S of t is E minus 2t ut, u of t. So that will give us negative infinity to positive infinity, epsilon minus 2t, u of t, epsilon minus st dt. Now recall that the u of t is something like this. So once we multiply the unit step function by our signal, it's going to truncate all signal parameters between negative infinity to 0, so that signal parameters from 0 to positive infinity will exist. So it means that this automatically changes the limit of integration. So we already discussed that in our previous lecture. So then this will now become integral, taking on values from 0 to positive infinity, epsilon minus 2t e minus st dt. So the u of t has been taken care of. Okay? Now, so with this, we can also compress this to now read 0 to infinity. So well, we want to say positive infinity, positive 0, right? Because from the Gibbs phenomenon, something may happen between negative 0 and positive 0, okay, at the point of discontinuity. Okay, so we want to say positive 0, really. It's positive 0. So the point is, what is negative 0? Okay, now from 0 to positive infinity, epsilon. So with this, we now have minus, if we compress this, 2 plus s, 2 plus s. So that will give us minus 2 minus s, right? T dt. So once we integrate this is now going to give us negative 1 over 2 plus x, epsilon minus 2 plus s t, taking on values from 0, positive 0 to infinity. So this also will be the same thing as once t being infinity multiplies through this is going to give us infinity. So that will be negative 1 over 2 plus x, epsilon infinity minus epsilon 0, right? So negative, right? Negative infinity. So anything raised to the power of negative infinity will reduce to 0. So it means this is going to reduce to 0, while this is going to reduce to 1, right? So then this will now reduce to negative 1 over s plus 2, 0 minus 1, right? Which will be negative 1 over s plus 2 into bracket minus 1, which will give us 1 over s plus 2, such that the Laplace transform of this is the same as 1 over s plus 2, okay? Now, you see that this actually forms a Laplace transform pair, okay? Now, when you look up the table, you can find that in any standard test, or you could check it up on the internet. In the Laplace transform pair, you see that epsilon minus at u of t forms Laplace transform pair with 1 over s plus a. So let's assume I want to use Laplace transform pair, and we're given this. And then they said, well, what is the inverse Laplace transform of this expression? So all I need to do is to come to this expression. Then I look up this expression, but I will need some other parameters to tell is the region, for the region of convergence, or better still, is S less than or greater than, you know, a certain parameter, okay? So if it's less than, if it's greater than, then fine. But if, for instance, I'm given the condition that for this, the real value of S is greater than negative A, then this expression will hold. So all I need to do for me to be able to get S of t, I just need to evoke this formula. So I have been given A to be 2. So it will be epsilon minus A is 2, 2t u of t. So I'm back to this expression. So that is how to use the Laplace transform pair to generate the inverse Laplace transform when you are given the Laplace transform. Okay, so if they say, well, this is the Laplace transform of the particular expression, you need to invoke the Laplace transform pair like you have in the table, something like this, and then you apply it. Okay, so I'm just trying to run through a whole lot of details, but you have more information in your past videos. Okay, so I wouldn't want to waste too much time moving around on some details. Okay, now okay, So if that is that, then there's still something we need to deal with here. Okay. So what is the region of convergence? Is this system stable? Okay. So let's wipe this. So now we already have that the Laplace transform is the same as 1 over s plus 2. Okay. Now we have what we call poles and zeros. Okay. So I think I would want to, just quickly talk about the poles and zeros. So once I talk about the poles and zeros, I think then we are good to go. So usually the Laplace transform is given as a rational fraction, okay? Such that we have the numerator and the denominator. In this case, the numerator is 1 and the denominator is s plus 2. But in a general form, we usually have, say this is the same as a naught s minus z1, s minus z2, all the way s minus z, say n. Then for the denominator, say b naught, s minus p1, which are poles, s minus p2, all the way down to s minus pn. So the point is the root we have in the numerator gives us the zeros, while the roots we have in the denominator gives us poles. So what I want you to take note of here is that the root of the numerator polynomial z sub k in this case are called zeros. And the interesting thing is that the value of this zero forces the Laplace transform to 0, okay? So a 0 is a value that forces the Laplace transform to 0. So if the zeros of this numerator happen to be 0, then 0 over whatsoever will give us 0. So a 0 is a value that forces the Laplace transform to 0. Now, the roots of the denominator polynomial p sub k are called poles. Okay? And a pole is a value that forces the Laplace transform to infinity, forces the Laplace transform to infinity. So you imagine p, the roots here forms 0. So anything over 0 will be infinity. Okay? And now this is very important in that the poles and zeros, in terms of their importance, one, they dictate the stability of the system. And also, poles in the left half plane indicate stability, while zeros can also affect the response speed, and overshoot. Okay? So these are the significance of the zeros and poles. So now that we have this expression, so by the time we set the characteristic equation, which is the denominator, so we call the denominator, so when you get to control studies and all of that, in your higher studies, you'll see this is characteristic equation. This is very important. So with this, we're able to tell if the system is stable or not. So when we set the characteristic equation to 0, we're able to derive the pole. Now, if we equate the numerator to 0, we're able to get the zeros. So by the time we equate the characteristic equation, which is the denominator, to 0, so s plus 2 is equal to 0. So therefore, s is equal to minus 2. So it means that a pole exists at minus 2 in this expression. And this value is a value that forces the Laplace transform to infinity. So in other words, it forces the denominator of the Laplace transform to 0, because 0 forces the numerator of the Laplace transform to 0. The same way, the pole forces the denominator of the Laplace transform to 0. Okay? So now, if we plot this on the x-plane, let's plot this on the s-plane. This is the s-plane, right? And we are saying this is -2. S is -2 and -2. So it means that this is what we get. There's a line here, okay? But is this a right-sided or a left-sided signal? Now you recall that y of t is given as e minus 2t u of t. And this u of t is a unit step function. So this is right-sided, because it truncates all the signals on this left side, and we have signals on the right side. So it means that this is the imaginary axis. So it means that the signal is right-sided. Since it's right-sided, then the region of convergence is to the right. So we'll call this side the region of convergence. And one interesting thing you should notice this: when this region of convergence includes the imaginary axis, then it means that the system is stable. Okay? So with this, we have been able to tell that from the Laplace transform that this system is a stable system. Okay? Now, there are a few details we will need to play with, but okay, let's talk about the region of convergence. The properties. Let's change the color, okay? Properties of region of convergence. Well, the first property is that the region of convergence never contains any poles, okay? So when we have the region of convergence, if we have a pole here, we have a pole here. So it's either this forms a strip, so the region of convergence cannot contain a pole, okay? Now, a pole must not be inside the region of convergence. Then the second thing is that the region of convergence is always a region of the S-plane to the left or right of a vertical line or a strip between two vertical lines. So we can have left-sided, region of convergence is here. It could be right-sided. It could be a strip. Okay. The strip could be anywhere on the S-plane. Okay. So it could be something like this. Now, another property is that if S of t is left-sided, then the region of convergence is also left-sided. So if, for instance, the signal is this way, so we know that the region of convergence is going to be left-sided. And the same way, if the signal, the fourth point, if S of t is right-sided, then the region of convergence is also right-sided, like the example we played with. So if the signal is right-sided, then the region of convergence is also going to be right-sided. What if the signal is two-sided? Then we are going to have a strip, okay? So let's write this. So the fifth point, if S of t is two-sided, or better still, the sum
Sorry, sir.
of a left,
Sorry, sir.
yeah, just a
Please,
minute,
can you-
just a minute, of a left and right-sided signal, then the region of convergence will either be a strip or it may overlap or be a null. Okay, so we could have something like this, a strip that is like this, or better still, let's say this is the line, so it could be something like this. It could overlap. It could also be something like this, where it doesn't even overlap. Okay, and the final point, just before I'll take your question, if the signal is of finite duration, then the region of convergence will be the entire plane. So let's assume we have a signal like this. So this is a finite duration signal, right? So it takes on from values of 0 to possibly A. So the region of convergence is going to include every part except the part with negative infinity, so the part with 0, and except the part with positive infinity. But every other part here will be, so it's going to exclude x equal to 0, s equal to negative infinity, s equal to positive infinity. Other than these points, every other part of the plane will be the region of convergence. So please tell me, what is your question, please, before we move on?
Sir, it's not really a question. I just wanted you to quickly go to like the page before this one, so I can quickly take a screenshot because I didn't finish.
Don't worry, I'm going to upload the video, so you have nothing to worry about.
So
Okay.
my question is on the sigma.
Okay.
Like what analysis institute is equivalent, and considering the U of t, how you were able to like analyze it from minus infinity 0 to infinity back to infinity 0. I mean the boundaries.
Okay. Now, if I got that
So
right,
we're from second slide down. First slide.
yeah, this is negative infinity 0, then this is positive infinity, right? For a unit step function, right? So if I get you right, so how come are you talking about the limits of integration, how it moves from negative infinity to positive infinity to 0 to infinity?
Yes, sir. I mean from the integration given, we were having e of minus s of t of u of t, then the t. So like u of t was among like some, if you can refer to the last slide to better see the integral.
I'm sure you're talking about the last example.
Yes, sir.
Okay, where we had s of t equal to e minus 2t u of t, right?
Yes, sir. Integral to infinity.
So we have integral negative infinity to positive infinity, e minus 2t u of t, right?
Yes,
E
sir.
minus st dt. Okay, so what is it about it?
I mean, how you were able to eliminate u of t?
Yeah,
Is
so
there like a principle?
it's multiplying the signal. Yeah, so u of t, now this is u of t is the same as this, right? This is signal multiplication. So I have es, okay, I have, okay, let's do it this way. I have e minus 2t u of t, now e minus st dt. So this is going to give us e minus 2 plus st u of t, right?
Yes, sir.
So this is the integral limit then dt. Okay, but this signal has to multiply this signal, and it's a unit value. This is also equal to 1, right? It's equal to,
Okay.
it's equal to
Oh.
1. It's a unit step function. This is a unit step function. So it's
Thank you, sir.
1. Yeah, so since it's a unit step function, but its value will truncate all the negative part of the signal, right?
Yes,
So
sir.
all the negative infinity to 0 of this signal will be truncated, but the magnitude of this is 1, right? So once
Yes,
that
sir.
happens, automatically, we are going to be having signals that exist from 0 to positive infinity.
Oh.
So all the values of the signal from negative infinity to 0 is equal to 0, right? They are on 0
Yes,
plane.
sir.
So from 0, then from point 0, there's discontinuity here, right? And then the magnitude of the signal becomes 1, isn't it?
Oh.
All right?
Thank you, sir.
Okay, so from there, we now have 0 to positive infinity, e minus 2 plus st times 1 dt, right? So this would be
Yes,
the
sir.
same as integral 0 to infinity epsilon minus 2 plus st dt. Is that clear?
Yes, sir. And sir, what about the sigma? Like, what analysis gave the equivalent? We're having sigma plus complex multiplied by
Sigma plus what? In what now? In which of the expressions? Not this question, right?
Yes, sir. The other one, the previous one to this,
Okay,
the one before this question.
when we were
Like,
evaluating the Laplace transform,
yes, sir. Like we're having x equals to sigma
integral
plus
s of
complex.
t epsilon minus st dt. This is Laplace transform, negative infinity to positive infinity, right?
Yes, sir.
But we know that s is the same as sigma plus j omega, right?
Yeah, my exact question is on this. J plus omega, sigma plus j plus omega. Are we able to make it equivalent to the signal?
I don't understand. Equivalent to the signal. How do you mean?
The sigma plus j damping function equal to s, the signal.
I think he's talking about the inverse Laplace transform. That formula that had the limit as sigma plus j infinity, then the other is equals to, yeah, that's
S of x 1 over 2 pi j, right?
Yes, sir.
Sigma minus j omega, then sigma plus j infinity, s of s epsilon st ds. So what's wrong with this?
I mean, like, is there so you didn't show how we got the s equals to sigma plus j omega.
I don't get it.
So, sir, I think it's, excuse me, sir.
Now this is a formula for inverse Laplace transform, and we could derive this, but very rigorous, right?
Oh, okay, sir. It is quite clear.
Okay.
So we just had to.
Is that clear? Or you want us
Thank
to
you, sir.
move on?
It is all right, sir. It is fine now.
Okay.
Thanks, sir.
Okay. Okay. So I think right now we are almost done with the Laplace transform, but there are quite a number of Laplace transform pair I would love you to look up from your materials, also in our previous notes. So I'll just mention a few. So we have S of t in the time domain, S of s, and then we have the region of convergence. So for the Dirac delta function, the Laplace transform is a unit value, and this exists for all values of s, right? Now for the unit step function, the Laplace transform is 1 over s, okay? And then for the real values of s greater than 0, Now, when we have epsilon minus at u of t, this is the one we resolved. We have 1 over s plus a, but then s exists at some point greater than minus a. And then this is a right-sided signal, right? Now, when we have negative epsilon minus at u of minus t, then we also have the Laplace transform to be the same as 1 over s plus a. But the point is s exists at some point less than a. This is a left-sided signal. Now, we can move on and on in the Laplace transform table. T to the power of n, t super n u of t will give us n factorial over Sn plus 1. And here, the region of convergence, or the real value of S rather, is some value greater than 0. The same with sine omega naught t, u of t. We have omega naught over S squared plus omega naught squared. And the real value of S is at some value greater than 0. So we can go on and on, okay? But so that whenever you are given the Laplace transform and you're able to walk around it to get something close to this, then you can use this to invoke the time domain equivalent based on the conditions for the region of convergence. Okay, so I think we have an example. We just play with that example and then we can move on. Okay.
So, what did you write in the last, what do you call it? Laplace transform, the frequency domain. That rho, or rather the time domain.
Rho.
That's this one, t raised to power n ut.
Uh-huh.
Yeah, what do you write? Is that Sn?
It's S. Well, you see this in your standard materials, okay? You can derive them, you can solve them. So it's also in our lecture note on Laplace transform. You can look up the lecture note, the video online. So you have all of this, more than this, okay? So it's just, I'm just trying to recap because we are going to evoke some of these rules right now to, get the inverse Laplace transform. And another interesting thing is that for us to be able to resolve the inverse Laplace transform, you need to recall your partial fraction decomposition, technique. Okay, so we're going to be doing, little partial fraction decomposition, or you could use some other mathematical tools, you are comfortable with. Okay. Okay, I can see Alawude's hand up. Can you please tell us what you want to share with us? Okay. So let's assume we have the Laplace transform given as 2s plus 4 over x squared plus 4x plus 3. And now we want you to resolve the Laplace transform in this case. Okay, so we need a rational function. Okay, so what are we going to do here? Okay, so we'll have to resolve this. And for us to be able to solve this, we'll have to use partial fraction decomposition. And if you recall from your partial fraction, you have quite a few concepts to play with in your partial fraction. You have linear factors. So you want to revise that. You have repeated linear factors. You have quadratic factors. Then you have repeated quadratic factors. Then you have improper fractions. Okay, so you want to look up to see, well, how is this partial fraction looking like? So which of these methods will apply? Okay, so from here, this is kind of linear, right? So if that's that, so by partial fraction decomposition, Well, I don't want to go into this. This is pure mathematics, so you want to revise all of these in case what you have does not look like this. So this could be something that could be resolved using repeated linear factor, or using quadratic factors, or using repeated quadratic factors. But I understand you've played with partial fraction already in mathematics, isn't it?
Yes, sir.
Okay, good. So
Yes, sir.
So I think that makes things easier for us. So s of x will now be the same as 2s plus 4 over x squared plus 4s plus 3 will be the same as, well, we can factorize this. So 2s plus 4 will give us s plus 1, s plus 3, right? So this will give us a over s plus 1 plus b over x plus 3. So if we multiply through by what we have here, the denominator, so s of s will be the same as 2s plus 4 over s plus 1, s plus 3 equal to a over s plus 1 plus b over s plus 3, all multiplied by x plus 1, s plus 3. So this will multiply through this, that will be 2x plus 4 will be the same as a. This multiplied by this will be a into bracket s plus 3 plus b x plus 1, right? So we have decomposed that. And then we could expand this such that we now have ax plus 3a plus bs plus b. So this is going to give us a plus b x, then the constant will be 3a plus b. So if we should take for the constant, or for s, so we can now resolve this into simultaneous equations. So this is 2s plus 4, right? So the constants that are common will be a plus b is equal to a plus b is equal to 2. Then for the constant, for this constant, 3a plus b is equal to 4, right? 3a
Yes.
plus b is equal to 4. And once we resolve this simultaneous equation, we see that a is equal to 1 and b is equal to 1. So from this, it means that our Laplace transform given as 2x plus 4 over x squared plus 4x plus 3 is the same as 1 over x plus 1 plus 1 over x plus 3, right? So with this, we can now invoke the Laplace transform pairs we talked about, okay? So let us wipe all of this. Okay, I can see one hand up. Nee, tell us, please.
Good morning, sir.
Good morning.
In this example here, as we are trying to decompose the partial fraction, you put in bracket 25 plus 4 and all those things that are there. Why did you put at the end s plus 1 st? Why did you? Okay. No, to the right of your screen a bit.
Yeah, here.
No, down.
Yeah.
No,
No,
scoot to the right a bit.
S plus b that I wrote there. When it was multiplying everything through by s plus 1 times s plus 3. Yeah,
Okay.
that's
Okay. All right.
So
Thanks.
this will truncate this. So we have this. This will truncate this. So it will remain s plus 3 times a. So this now times this again. So that will x plus 3 times x plus 3, they will truncate each other. So it will be b times x plus 1, right?
All right. That's fine.
Yeah.
Thank you, sir.
Okay, you're welcome. So so now we already have that 2x plus 4 over x plus 1, s plus 3 is the same as 1 over s plus 1 plus 1 over s plus 3. So we've been able to resolve these expression, okay? To say, well, this is what it is. And this is close to what we can use the Laplace transform pair to resolve, isn't it? So let's assume our region of convergence, sigma, the damping factor is greater than -1. Okay? Now, if it is greater than -1, so we can draw that on the x plane. Okay, this is j omega, this is sigma. So if it is greater than, this is -1. So if this is the region of convergence now, and they're saying that sigma is greater than -1, so it must exist towards the right, because anything beyond -1 is greater than, to the right is greater than -1, isn't it?
Yes, sir.
So it means this is a right-sided signal. So from this, we can tell that this is a right-sided signal. Now, if this is a right-sided signal, then we can invoke the Laplace transform, right? So from the Laplace transform pair, what do we get? We know that for a right-sided signal, E minus AT U of t is equal to 1 over S plus A, right? So now that we have been given this condition could vary, okay? But for this first instance, we have been given this condition and we have been able to plot it on the S plane. We have seen that it's right-sided. So for right-sided signal, we know this is what we get, right? So we can now generate the inverse Laplace transform of this. So in this case, A is equal to 1 here, and in this case, A is equal to 3, isn't it? So it means that the inverse Laplace transform S of t, in this case, will be epsilon minus A is 1 times t is t, U of t, plus epsilon when A is 3 minus 3 t, U of t. Okay, so U of t is common, so we can also rewrite this as epsilon minus t plus epsilon minus 3t all into bracket U of t. So this is the inverse Laplace transform of this expression given this region of convergence. Right? Is that clear?
Yes, sir.
And
Yes,
now,
sir.
and now we can plot to see if the system is stable. Now, if we should equate the roots of these expressions, the denominator to 0 will get the poles, right? So for the first instance, s plus 1 is equal to 0. So s is equal to -1. S plus 3 is equal to 0. So s is equal to -3. So we have a pole at s equal to -1 and another pole at s equal to -3. So we can now plot that to see that, okay, this is -1. So we use star to denote a pole. Zeros are denoted with a circle, while poles are denoted with a cross, right? Then at -3, we also have another pole. But we understand from the properties, and we know it's a right-sided signal. We also understand from the properties of region of convergence that the region of convergence must not contain a pole. So the region of convergence cannot start here. If it should start here and go to the right, then there will be a pole in the region of convergence. So the region of convergence we always can start from this point to the right, so that there is no other pole existing here. Is that clear?
Yes, sir. Yes, sir.
So, and this is j omega, and this is sigma. And it is said that if j omega is included in the region of convergence, it means the system is stable. So now this is the region of convergence, and the axis that the j omega axis is inside the region of convergence, then it means this system is also stable. Is that clear, please?
Yes, sir.
Please come again, sir. Please come again, sir.
Now you see that the j omega, now the region of convergence is to the right, right? And now we already know that if the region of convergence contains the j, or includes, let's put the word includes, the j omega axis rather, then the system is stable. And in our case, j omega axis is in the region of convergence, so it means this is stable. Okay? But don't forget, we said that the damping factor determines the region of convergence and the stability of the system. So let us change the condition for the region of convergence and say, well, the region of convergence is, say, less than -3. What are we going to get? So let us try that out. So in this case, we have s of x equal to 2x plus 4 over x squared plus 4x plus 3. We already resolved this, that is 1 over s plus 1 over x plus 3. So let's assume sigma is less than minus 3. So if we plot this, for instance, this is minus 3. So all of this is greater than. So when we say minus 3, if it is less than minus 3, so the region of convergence must be somewhere around here, isn't it? Because those values are less than minus 3. So technically, we are able to tell from this expression that this is a left-sided signal. Isn't it? And for a left-sided signal of this form, we know that from the transform pairs, negative epsilon minus at u of minus t is the same as 1 over s plus a for left-sided signal, okay? So with this, we should be able to tell s of t, the inverse Laplace transform of this expression will now be negative epsilon when a is 1 minus t, u of minus t, plus minus epsilon minus when a is 3t, u of minus t, right? So minus times minus, so that will give us minus epsilon minus t, u of minus t, minus epsilon minus 3t, u of minus t, right? And we have this in common, so this can be the same as minus epsilon minus t plus epsilon minus 3t, u of minus t. Okay, so now we can plot the region of convergence. So we want to know if this system is stable, right? So we already know that we have a pole at s equal to minus 1. We also have another pole at s equal to minus 3. So we have minus 1, minus 3. And we know that it's a left-sided signal, and the region of convergence must not contain another pole. So we cannot start from here. So since it's left-sided, so the region of convergence is going to look something like this. So you see that the region of convergence does not contain j omega. So it means this system is not stable, right? Is that clear?
Yes, sir.
Yes, sir.
Okay, good.
Yes, sir.
So I think there's another example in the other videos we have online. So you just look up the other examples. It's the same process. There you want to look up the condition for sigma such that it is less than minus 1 and also greater than minus 3. So here you are going to get a strip. Okay? You're going to get a strip, minus 3, minus 1. Okay? So you can play with it using the same analogy. And we already know that the significance of region of convergence is such that it helps us understand system stability. And you now see that this damping factor is a critical factor in determining the stability of a system. Is that okay? Is that
Yes, sir.
yeah?
This sigma that is between minus 3 and minus 1, it means that the system is not stable, right?
It's not stable because it does not include the j omega axis. So if the j omega, if the strip was here such that it includes the j omega axis, it will be stable. But since it does not include the j omega axis, then it's not stable.
And also, the sigma, the value, would it be given to us as part of the question?
Oh, you are looking at questions, but we are looking at you designing systems as an engineer. Okay, so we are not talking about exam at this point. We are looking at you applying this in terms of designing your system. So when you are designing practical systems that will address local problems, then you should be looking at designing stable systems. Okay, that's what we are more interested right now. Is that okay? Yeah. So you don't want to design systems that will overrun the world. You want to design systems that will make the world an amiable place to live in, okay? Okay, so any other question? Okay, we've addressed Kelvin's question, right? So you may want to drop your hand. Okay, so I think now we can look up Z transform, which is the same as Laplace transform, only that here we are talking in terms of the discrete time systems. So we just played with the continuous time system. So we just run through. It's about the same thing. So in this case, we have an LTI system, but this time not a continuous time, a discrete time LTI system, which is characterized by h of n. And then we have the input s of n into the system. And then our output y of n is going to be h of n convolved with s of n. Okay? Okay, Kelvin is asking another question.
No, sir, this is my first question, sir.
Okay, so tell us.
Okay, sir. So, sir, what I wanted to ask was about the strip. Does that mean that we get a strip region of convergence if our range for damping factor is a range and not a value?
Yes, if it's a range, we get a strip, or we get we could also get a null. Okay, so it's either it closes in if we have a right-sided, left-sided closing in. So at times the region of convergence could spread out and not spread in. So depending on the condition. So you want to be sure what you are looking at, the positioning of the right-sided and left-sided signal. So if the positioning of the right-sided and left-sided signals are in the opposite direction, so you may get something like this. You may get a strip that looks something like this. You may get this. Okay? But depending on the positioning of the right-sided and left-sided signal, you could get something that looks exactly like this. So you have to observe those differences.
All right, sir. But, sir, if our positioning is like the first diagram you drew, does it mean it can be stable since it also
it includes it includes the region of convergence, yeah? Yeah.
Oh, okay. Thank you, sir.
You're welcome. Only that you now have to also figure out some other things that may result in overshoot, and there are a lot of things to now look into. Okay? Yeah, because when you also, now we're only considering examples that includes poles. You could also have some zeros, and having zeros could result in overshoot and could cause some disturbances in your system. Okay, so that's where you now have some other activities to stabilize your system. Okay, you have controllers. You want to bring in controllers. So as you progress in your system and you begin to take your study in control systems and all of that, you are going to go way into things like that. Okay, so there's more to stability of a system. Is that okay?
Yes, sir. Thank you, sir.
You're welcome. So it means that in this case, we have y of n being the same as h of n, convolved with s of n, for which n is the same as k. Then we can now take that this is the same as the sum of h of k, s of n minus k. Okay? So for k taking on values from negative infinity to positive infinity. Okay? But now we know that the eigenfunction in this case is the same as z of n. Okay, so z sub n, super n. So if z super n is the eigenfunction, it is also a complex exponential sequence. Okay, so this function being an exponential, or better say complex exponential sequence, we can now say that y of n is the same as the sum of h of k, z n minus k, for k equal to negative infinity to positive infinity. And this is the same as sigma h of k, z super n, z minus super k. Okay? And in the same vein, we can also bring all of these which are in common. So z super n sigma h of k, z minus k will be the same as h of z, z super n. So in this case, h of z is the same as sigma h of k, z super minus k, for k taking on values from negative infinity to positive infinity. And this expression, which is the eigenvalue and the response of the system, is the Z transform of the discrete time signal. Okay? Now, just the same thing we did earlier. So in a more general format, the Z transform is given as sigma, n taking on values from negative infinity to positive infinity, S of n, Z to the power of minus n. Okay, so this is the Z transform. And the inverse transform, the inverse Z transform, will be the same as 1 over 2 pi j. This is a closed integral, closed contour, S of Z, Z n minus 1 dz. So in this case, C in this case is a counterclockwise contour of integration enclosing the origin, okay? And for ease of evaluation, once again, we want to use the transform pairs rather than this inverse Z transform formulation, okay? So this is Z transform, okay? Okay, so if that's what it is, then we can now progress to look up the region of convergence. Now, so far in the last analysis, we show that the imaginary axis is this way, then the real axis is this way. But for Z transform, this imaginary axis is seen to have folded into a circle, so that we now have something like this, where this circle is the imaginary axis, while this is still the real axis, okay? So this point is known as the high positive frequency, high positive frequency. So in the same way, this side is known as the high. I'm just comparing X plane, Z plane, right? Positive frequency, right? So this part is high negative frequency. This side is also high negative frequency, okay? And this point, this origin is the DC, which is the zero frequency, okay? And this point, in our case, for the Z transform is the DC, which is a zero frequency, okay? So you should know that Z is the same as epsilon j omega, okay? Because we have the imaginary axis, which is j omega, folded around this axis. And in the same way, for the region of convergence, properties of the region of convergence. Now, one, we already know the region of convergence never contains poles, right? Region of convergence never contains poles. And when we have a right-sided signal, for instance, then the arrow, the region of convergence is something like this. Let's assume this is one pole. This is another pole. The region of convergence is outside the outermost circle, okay? And for a left-sided signal, so let's assume we have this first circle, then we have another circle. For a left-sided signal, this is one pole, this is another pole. It's usually in the innermost part of the innermost circle. Okay, so it's inside the innermost circle. So take note, right-sided signal is outside the circle. Left-sided signal, the region of convergence is inside the circle. So when we have a two-sided signal, so let's say two-sided signal or sum of right and left signals, so we usually have a donut, okay? So it could be something like this. Times it could even be something like this. We have the region of convergence in and out, okay? It could be something like this. Now, the fifth point here is that for a finite duration signal, the region of convergence is everywhere except the point where we have negative infinity, where we have 0, and where we have positive infinity. So every other part is the region of convergence, okay? Now, I think that's about it. So we may want to evaluate one simple example. So let's assume we have this signal S of n taking on these values. So we have okay, something just went wrong here. Okay. So let's assume this is 3, this is 2, this is -1. So you already know about this. So this is -1 discrete signals. This is 0, then this is 1, and this is 2, right? So this is n. So we want to find the Z transform of this. So we already know that the Z transform is the same as a sum taking on n from -infinity to +infinity, S of n, Z to the power super minus n. But here the limit is -1 less than equal to n less than equal to 2, right? So this now Z transform will be the same as n taking on values from -1 to 2, S of n, Z inverse n. So from this, S of -1 is 3, the magnitude is 3. So we have 3. Then Z inverse -1, right? Z -1. So we have minus, then n is -1 here. Plus the next point, the magnitude is -1. Then Z -0, right? Is 0, n is 0. Plus the next point is 2. The magnitude is 2. Z -1. Then the next point, the magnitude is 0. Then Z -2. Okay? So this will give us 3Z1, that's +1, right? Minus, minus. Then this will give us -Z to the power of 0 plus 2Z -1. Then 0 times all of this plus 0, okay? So anything to the power of 0 is 1. So that's going to give us 3Z -1 plus 2Z inverse. So our Laplace transform in this, I said Laplace, Z transform rather, in this case is 3Z -1 plus 2 over Z, right? Because this is inverse of Z, okay? Is that simple and straightforward? Very simple and straightforward, okay? So we could play with another example. Okay, let us try to evaluate another simple example. Say Sn is the same as 1/4 to the power of n u of n. Okay, so we want to evaluate the Z transform. So we already know that Z transform is the same as n taking -infinity, S of n. Okay. So this will now give us, we know S of n to be this expression. So that will be the sum, n taking on -infinity to +infinity, 1/4 to the n u of n, Z -n. So we already know what the unit step function will do here. Is going to change our limit of integration. So we now have n to be the same as 0 to +infinity, 1/4 to the power of n, Z to the power of -n. Okay? So in this case, we have sigma n equal to 0 to +infinity, 1/4 Z inverse to the power of n. So we have been able to compress this. And you recall that this is similar to the sum of infinite geometry. So which we played with in one of the examples. I think one of our colleagues here draw attention to that. Okay, so A arrow n, which is the same as n equal to 1 to infinity A arrow n -1. which is same as A over 1 minus R, where A is the first term and R is the ratio. So in our case, this is R. Everything we have here is R, okay? Because that's to the power of n. So it means that the first term is 1, which is not shown. So we can now rewrite this to say A is the same as 1, and then R is the same as 1 over 4 Z inverse, okay? So then, once we plug that into this expression, so our Z transform will be the same as 1, which is first term over 1 minus R, which is minus 1 over 4 Z inverse. And this is going to give us 1 over 1 minus 0 0.25 Z inverse, right? Which is the same as, you know, whatsoever you want to place it. So 1 over 1 minus 0 0.25 Z, whichever way, okay? So you will notice that at Z equal to 0 0.25, the denominator will reduce to 0, and then the Z transform will be infinity, okay? So if Z is the same as 0 0.25, this will be 1. 1 minus 1 will be 0. So to have a finite Z transform, the Z transform, then mod Z must be greater than 0 0.25. So once it is 0 0.25, the Z transform will be infinity. So that will be sufficient condition. This would be a sufficient condition to have a Z transform. So in the same way, we have the transform pairs, okay? And we are also able to evaluate the inverse Laplace transform and also tell the region of convergence. But I'll just mention a little detail.
Wait.
Now, for us to be able to evaluate the region of convergence, then the region of convergence must contain the unit circle. Okay, so I'm going to take one example. Okay, so I'm going to take one example that that will deal with that. So let us determine the Z transform region of convergence for this given example. So let's assume we have S of n being the same as 1 over 2 and U of n plus 1 over 3 and U of n. And then we have the condition 1 over 3 less than mod Z and 1 over 2 less than mod Z. Okay? Now, from the Laplace transform pair, just like we have, from the Z transform pair rather, just like we have in the Laplace transform pair, we have an U of n is equal to 1 over 1 minus AZ inverse, okay? So this is same as Z over Z minus A when Z is greater than mod A, okay? So for this, so we can now go on to resolve this. So that 1 over 2 to the power of n U of n, this is square bracket, please, is equal to 1 over 1 minus 1 over 2 Z inverse, which is the same as Z over Z minus 1 over 2 for mod Z greater than 1 over 2. Now, we also have 1 over 3 and U of n equal to 1 over 1 minus 1 over 2 Z inverse, which is the same as Z over Z minus 1 over 3 for mod Z greater than 1 over 3. Okay? So in this case, mod Z is greater than 1 over 3, mod Z is greater than 1 over 2. Okay? So based on that condition, so we can now add them up. S of Z will be equal to Z over Z minus 1 over 2 plus Z. So let's designate to differentiate between 2 over Z minus 1 over 3. So we can resolve this to say Z into bracket Z minus 1 over 3 plus z into bracket z minus 1 over 2 over z minus 1 over 2 into bracket z minus 1 over 3. So this will give us z squared minus z over 3 plus z squared minus z over 2, right? Over z minus 1 over 2 into bracket z minus 1 over 3. Okay, so and you have to wipe this part. Wipe this part. So if we take things off from here, so we have 2z squared minus 2z plus 3z, taking LCM over 6 over z minus 1 over 2, z minus 1 over 3. So this will give us 2z squared minus 5z over 6 over z minus 1 over 2, z minus 1 over 3. So this will give us 2z into bracket z minus 5 over 12 over z minus 1 over 2, z minus 1 over 3. So this gives us the zeros, and this gives us the poles. So in this case, we are going to have some zeros and poles. So, so for the zeros, 2z equal to 0, 2z equal to 0. So there, z is equal to 0. And then also, we have z minus 5 over 12 is equal to 0, such that z is equal to 5 over 12. Now for the poles, we have z minus 1 over 2 equal to 0, such that z is equal to 1 over 2. And z minus 1 over 3 is equal to 0, such that z is equal to 1 over 3. So a 0 exists at 0, and zeros exist at z equal to 0 and 5 over 12. And poles exist at z equal to 1 over 2 and 1 over 3. So now we can plot, okay? So let's wipe this. So let us wipe this, and then, so let us plot. So now we have a 0 at 0. So let us use some other color. Let's use blue to indicate the zeros. We have a 0 at 0. And then we also have a 0 at 5 over 12. That's positive value. So let's say 5 over 12. That's where we have a 0. Now, we also have, we now have a pole at half. So 5 over 12 is less than half. So let's say this is half. 1 over 2. Then we also have a pole at 1 over 3. So 1 over 3 will be somewhere around here. 1 over 3. And this is 5 over 12. This is 0, right? And we already know that the region of convergence does not include this, does not include poles. So the region of convergence is going to be somewhere around here. It's a circle, don't forget. Okay, so it's a circle. Okay, but note that z from our analysis, z is greater than 1 over 3. Z is greater than 1 over 2, right? So it means that it is beyond 1 over 2. So it's spread out. So the region of convergence is somewhere around here, ROC. But is this system stable? Now, if this is 1 over 2, let us try to extend this line. Okay, let's try to extend this line. Try to extend this line. So if this is half, so probably this is 1. okay? Now, it means that the region of convergence extends to this. So let's assume we draw our unit circle. Let's use another color to draw a unit circle. So let's assume this is our unit circle. But we have that the region of convergence extends beyond half. So you see that the unit circle is in the region of convergence, right? So since the unit circle is in the region of convergence, the system is stable. Okay? Is that clear, please?
Yes, sir.
No.
Yes, sir.
Sir.
Okay, so now let's assume the region of convergence. Let's assume we have something like this, and this is half, and the region of convergence is inside this circle. Is this system stable or unstable?
It is unstable, sir.
Perfect. It is unstable because if we should draw the unit circle, for which this is 1, the region of convergence does not include the unit circle. So for us to know if the system is stable when analyzing Z transforms, the region of convergence must include the unit circle for the system to be stable. Okay, good. So one more thing we are supposed to discuss today is Fourier transform. So we're able to conclude on Fourier on the transforms. But unfortunately, we have just about less than 10 minutes to end the class, and I don't think we'll be able to run through the Fourier transform within that time frame, but I will just introduce it, okay? I'll just introduce it. So Fourier transform. Now, Fourier transform follows directly from the Laplace transform, okay? The continuous continuous time system. We already established that the Laplace transform is given as negative infinity to positive infinity s of t, epsilon minus st dt, such that s is the same as sigma plus j omega, okay? So when we spread this out, we now realize that this is the same as negative infinity to positive infinity, s of t, epsilon. We already resolved this, minus sigma plus j omega t dt, which is the same as in the negative integral negative infinity to positive infinity, s of t, epsilon minus sigma t, epsilon minus j omega t dt. And now we have s of s is the same as integral negative infinity to positive infinity, s of t, epsilon minus sigma t, epsilon minus j omega t dt. So when the damping factor sigma is the same as 0, what do we get? S of s will be the same as negative infinity to positive infinity, s of t, epsilon 0, right? S of minus j omega t dt. So this is going to give us negative integral negative infinity to positive infinity, s of t times 1, epsilon minus j omega t dt. And then s of s will now be the same as negative integral from negative, taking limits from negative infinity to positive infinity, s of t, epsilon minus j omega t dt, which is our Fourier transform. Okay? So when the damping coefficient is 0, then we have our Fourier transform. And you now observe that this expression that describes the Fourier transform is only dependent on the frequency and not on the damping factor, okay? So because you remember that the damping factor helps us to analyze the region of convergence and all of that. So that's why the Laplace transform is used to analyze systems, but the Fourier transform is used to analyze the frequency content of signals. Because all that we have here, all that we can deal with here is the frequency component, where omega is same as 2 pi f. Is that clear? Are you able to see the difference between the Fourier transform and the Laplace transform?
Yes, sir.
Good. Now,
Yes, sir.
if that is clear, so it means that our Fourier transform is the same as integral negative infinity to positive infinity s of t epsilon minus j omega t dt. Okay. And we can also say s of f will be the same as negative infinity to positive infinity s of t epsilon minus 2 pi f t dt. Okay, and the inverse Fourier transform follows directly 1 over 2 pi integral negative infinity to positive infinity s of omega epsilon j omega t d omega. Okay, and also we prefer to use our Fourier transform pairs to resolve our problems. Okay. Okay, that sounds good. And in the same vein, you recall, you now see that if we have to represent this in terms of the frequency and not the angular frequency, something will change. Okay. Now you see that here. Okay. So you see that we now have 1 over 2 pi integral negative infinity to positive infinity. So here we have s of f, for instance. So this would be epsilon j omega, no, not omega anymore, 2 pi ft d 2 pi f, right? So this will now be 2 pi comes out. So that will be 2 pi over 2 pi integral negative infinity to positive infinity s of f epsilon j 2 pi ft df. So this truncates this. So it's also equal to integral s of f epsilon j 2 pi ft df. So in some tests, you may see the inverse Laplace transform represented in this manner in terms of frequency, and then you not see 2 pi. So that's how it is worked out, okay? And if we should use a Riemann sum to express this, you now see that we have frequency. These are different frequency components. And you recall that when we have a frequency component being multiplied by whatsoever we have, then from what we made mention of in our last class, so long we have a complex exponential component multiplying a frequency, a signal component with its frequency value, then the magnitude and phase of that signal is altered. Okay, so that is why in signal processing, the inverse Fourier transform is used for the recovery of signals. Okay, and there we utilize the magnitude and phase information stored in the original signal. Is that okay? So I think technically the system is seen more like a filter. Okay, and if you look up the notes that we already have, you see that we talked about low pass filters, where, for instance, this is the cutoff frequency. So here we remove all the frequencies above the cutoff frequency. We use this for noise removal, interpolation and data smoothing. Then we also have high pass filters. Okay, so where, for instance, this is the cutoff frequency. So it removes all frequency information below this cutoff frequency. I'll use it for to remove DC or low frequency drift, edge detection and enhancement, Then we also have band pass filters. We'll have something like this. We have F1, F2. So it removes all information outside this range of frequencies, okay? So we use this for tuning in radio stations and audiographic equalizers. Then we also have the notch filters, okay? And for the notch filters, something like this. So we have F1, F2. So here it removes all frequency within this range, okay? And here we use it for removing noise at a particular frequency. Say we want to target 20 Hz. Okay, so we want to target, so you use it to remove noise at specific frequency values. So we also have some properties, linearity, duality, convolution, product, time shift, frequency shift, differentiation. I would love you to review the lecture notes we already have in that regard. And then in our next class, we'll try to review Fourier series, okay? And you see that by the time we take the Fourier transform of a rectangular function, what we get is a sinc function, okay? So we have examples in the videos online. So if you've got any, if you have any doubts, then we'll review them before we begin our interaction on Fourier series. But this is all about Fourier transform, really. So with this, we can say we've covered the transforms, the Laplace transform, the Z transform, and the Fourier transform. And we have a few examples in our previous video, so you want to look them up. So if you do not understand them, then we'll now walk around it. And then some of the verifiable Fourier transform pairs are also in the lecture notes. I think this is a good place to stop so you don't get oversaturated. So for now, any question, please, before we call it a day?
So you were talking about that we are going to look about Fourier series next week. I think we are talking about transforms. Why Fourier series?
Yeah, we are done with Fourier transforms. We just ran through it in a few seconds, and we were able to cover the details about Fourier transforms, how we are able to move from the Laplace transform domain to the Fourier transform domain. And the idea is that you have been able to see that in Fourier transform, what we are particular about is the analysis of the frequency content of the signal, because the damping factor is eliminated, has been eliminated, okay? And is a damping factor that helps us characterize systems, okay? But in Fourier transform, the component we have is omega, right? And that describes the frequency content of whatsoever we are trying to analyze. Okay, and looking at the Riemann expression, can look that up in the previous note as well. It's detailed. So if you do not understand, then we could take some questions in our next class before we begin. Then you see that it acts more like a filter. Okay, so it acts more like a filter. So with that, we are able to generate the expected signal given a particular signal. But you should understand that this applies to non-periodic signals. Okay, so if we now have to evaluate the frequency contents of periodic signals, then the Fourier transform will now scale down to Fourier series. So we'll see about that next week, okay? So as far as we're concerned, we've been able to run through transforms, the Laplace transform, the Z transform, and the Fourier transform in this class. Is that okay?
Yes, sir.
Okay, so I think,
Yes, sir.
so do have a great day. See you next week.
See you next week.
Yeah, bye for now.
All right.
All right for now.